Okay, well, today is the first time that we are going to try distance learning, where I'm going to try and help you understand physics over the computer. And so today I am going to start into chapter 21, which is entitled The Electric Field. Very important concept, somewhat difficult to grasp some of the ideas, but actually relatively simple to work with as soon as we get into it and start actually putting numbers to it. We're going to be in section 21.1 today, which is measuring the electric field. It also says creating the electric field, but really we don't create an electric field. This says force, that should say field. So before we talk about the electric field, let me take you back to something that we know somewhat, and that is a gravitational field. It's the only other field we know. Field means that there's a force that's at work in that region of space. If this is the Earth, and I were to take and put an object here, we know that it would fall straight toward the Earth. If I put it over here, it would also fall straight toward the Earth. And we would get a picture that would look something like this. And we could actually put lines in here to show which way it goes. This is a visual representation of a gravitational field. It's imaginary. It doesn't actually exist. And notice there's no actual lines. The field exists, but the lines don't. If you were to take and put an object here, and these were taken away, even the Earth was taken away, I could predict where this would go by following these two lines and try and bring it right in there. By the way, these would all meet at the center. This is a picture of a field. Two interesting things about the field. The first one is the closer the lines are together, the stronger the field. So the field actually decreases as it goes out. And it decreases in a very consistent way. The strength of the gravitational field decreases by the square of the distance. And we'll come back to that in a minute. But what we would say is the gravitational field, if I was right here, and if I moved twice as far out, this would be 1/4. It's the field divided by 2 squared. So since the distance is now 2, we'd be 1/4 of that. Okay. Now, what's interesting about this is if you take Newton's second law and we apply it with gravity, F equals mg, which we would call the weight of the object. G here is F divided by m. And all of a sudden, instead of the typical units, we would say G is 9.8 meters per second squared. This becomes 9.8 newtons per kilogram. And that tells me more about the field than just the acceleration. In other words, if I was to take and put, say right here, right above the Earth, it doesn't look like it on this picture, but I put 1 kilogram here. That 1 kilogram would be drawn toward the Earth with an acceleration of 9.8, but the force of that would be 9.8 newtons. That's because our gravitational field, G, is F divided by m. It's 9.8 newtons divided by 1 kilogram. If I change that and make this 10 kilograms, we still are 9.8 newtons per kilogram, but now because we have 10 kilograms, this one would fall toward the Earth and apply 98 newtons of force. G, in other words, can be thought of just as much as a force per charge than as an acceleration. By the way, I said we'd come back to this. If I take this same box and put it right here, and this was 9.8 newtons, say we had 1 kilogram. If I moved that twice as far away, it would be 9.8 newtons divided by the force on that object by 2 squared, which would be 2.45 newtons. If we took it 3 times as far away, it'd be 9.8 newtons divided by 3 squared, and about 1.09 newtons. Now, I know that was a little bit weird, but what we're trying to do is extrapolate, because when we move to electric fields, the problem with the Earth's gravitational field is the Earth is so big that unless you are really, really high above it, even if we put satellites up, they have virtually 9.8 meters per second squared, or 9.8 newtons per kilogram. But electric fields are not like that. So let me transition over to electric field. If I was to take a positive charge and put a big positive charge, put a little positive charge, so it's kind of like the Earth and a mass. Because these are the exact same charge, this would actually go this direction. And by the way, if you look at this, except for the fact that the arrows are going out, that's exactly the same thing as what would happen with the Earth. These lines would tell us where a positive test charge would go and where it would move to. It obeys the inverse square law. The strength decreases as these get further apart. The interesting difference is if this was positive and this was a negative test charge, it would look exactly like Earth's gravity coming in. All right? Now, this field is called the electric field, just like this field is the gravitational field. And the symbol for the gravitational field is E is equal to F, is E, I should say. And this symbol means electric field intensity. And it is measured by doing F over Q. And your book will actually say F over Q1. So the idea is we've got Q2 here, and we have our little test charge is Q1. What is Q1 experiencing? And it's experiencing some force, and the ratio of force to charge is our electric field intensity. And so if you look at this, it's the exact picture of this right here. G is F divided by M. Masses are what's attracted in the gravitational field. E is F over Q. I know Q looks like G, which is a shame, but E is equal to F over Q. Turn that so we can see a little bit better. And that tells me, oh, by the way, this is electric field strength or intensity. The strength of the electric field, we simply measure the force on one particular charge. The units here would be newtons per coulomb, as opposed to newtons per kilogram over here. And that would be E, it would be a force. Very, very simple problems. If I told you that you have a force of 20 newtons on a 2 coulomb charge, and they ask what's the electric field intensity, it's 20 newtons divided by 2 coulombs, it would be 10 newtons per coulomb. In other words, what we'd be saying is if you had 10 newtons, any charge, you're going to have 10 newtons per coulomb. So in this case, it was 2 coulombs, 20 newtons. If I had had 5 coulombs, that would have been 50 newtons. That's all that's saying. We, of course, could rearrange that. I could say that I've got electric field intensity of 2 times 10 to the negative 3 newtons per coulomb, and I have a charge of 5 coulombs. What is the force? And we would simply have to rearrange that equation. E is equal to FQ, so force is EQ. By the way, EQ would be equivalent to mg. M is equivalent to the Q. G is equivalent to the gravitational, in this case electric field intensity. Plug the numbers in and you'll have it. 2 times 10 to the negative 3 newtons per coulomb times 5 coulombs would be 10 times 10 to the negative 3. Sorry, you can't see that real well. It would end up being, force would be 10 times 10 to the negative 3 newtons. So that's pretty easy to work with it, but it's the idea that's important. And we'll stress that as we go. Secondly, there is another interesting equation that pops up, and that is if it is true that E is equal to F over Q, and we're going to put Q1, it's Q2 and Q1 which are what we've got. So I've got some Q2 here, and I've got a Q1, and it's experiencing the force. Over here, I had to tell you everything you needed to know. I had to tell you what the number of, what the electric field intensity was and what the charge was. But we can actually combine two equations, and that is this one from last chapter. And if I simply take force and replace it here, the electric field intensity can be K Q1 Q2 over R squared over Q1. The Q1s will cancel. You can check my algebra later. And what we get is this. Now this is really interesting. What it's saying is the electric field intensity does not depend at all on Q1. It depends entirely on Q2. And it depends entirely upon the distance we are from Q2. K, you remember, is 9.0 times 10 to the 9th newtons, newtons meters squared per coulomb squared. So let's do one of those problems, and then I am trying to keep these videos short. Let's say you were told that an object is let's do 0.5 meters from a 200 coulomb charge. What is the electric field intensity or the electric field strength experienced by that? A charged object is 0.5 meters from 200 coulomb charge. What is the electric field intensity the object experiences? Plugging it into our equation, E is equal to K Q2 over R squared. In this case, this would be 9 times 10 to the 9th newtons meters squared per coulomb squared times 200 coulombs divided by 0.5 meters squared. And by the way, this can be a huge number. In fact, I probably should have made this much, much smaller, but for the purposes of what we're doing, it doesn't matter. So this would be 9 times 10 to the 9th times 200 divided by 0.5 squared. A lot of students will forget the squared on there. And this would be 7 times 10 to the 9, 10, 11, 12 newtons per coulomb. Okay? Now, if they said the charge on Q1 is, let's say, 1 times 10 to the negative 10 coulombs, what force does it experience? The answer would be that back to the other equation, this one, force is equal to E times Q1. Notice the electric field intensity, 7.2, by the way, not 72, 7.2 times 10 to the 12 newtons per coulomb times 1 times 10 to the negative 10 coulombs. You would actually end up with 720 newtons of force on that particle. What is important is that it is not the Q1 that's determining the amount of force, it's Q2. Q2 produces a certain electric field that changes as the distance goes out. Now, what we're going to do in this, and it's in your folder, 21.1, there are, let me go and erase this. 21.1, you have problems with the answers in the back, 1 through 9 odd. What I'd appreciate you doing is doing these problems and then email or Google Doc them to me when you get them done. They do have the answers in the back, so you really need to show your work. In other words, just do your homework like normal. Take a picture of it and send it to me. All right, I know there are questions because that's fast, but I am trying to make these videos relatively short if I can. And we're at just about 16 minutes here. I'll try and keep them under 20. Next week, we're going to have the WebEx conferencing software. And during fourth period, we can ask questions, and you can ask me questions about this. So I'm going to go ahead and stop the video, read the chapter, the section, look at the pictures in there, try the problems, and hopefully we're good at that point. All right, see you later, and hope we see you soon, maybe after Easter break.